are on my webpage, so again, if you want to, people with laptops can follow along by downloading it from my webpage.
Okay, so our final speaker of the morning is I'm not sure what his title is, but yeah, maybe it's that. The factorization of p-adic Rankin L-series.
All right, thanks a lot. Thanks very much. Okay, so I guess I'll begin again by overlapping with my last talk and doing some review. These results that I stated will be used in this talk. So if we have a Dirichlet character, conductor n, and we can view it as a complex character by fixing an embedding of q bar into C, then its associated L-series is the sum of chi of n over n to the s, where you by fiat say that chi of a is 0 if a is not relatively prime to n. And the one thing that I'm not sure if I quite mentioned officially is that this has an Euler product expansion. We've seen that in several other talks. Okay, so now we have a special value formula for the value of this, for the leading term of this L series at s equals 0 and s equals 1. So for now, let's assume that chi is a non-trivial even character, which means that chi of minus 1 is 1, but chi is not identically 1. And if you consider the cyclotomic field of nth roots of unity, then we define this circular unit, which is just in the unit group of this cyclotomic field. Well, we tensor by q bar so that we can have exponents. So this might have alternatively written to the power of chi of a. So we think of this, coefficients and the right factor of this tensor product as exponents. There's a tensor product over z where the group operation here is multiplication and here is addition. And so this element that I've written down is in the chi inverse component of the action of Galois. Okay, so this is something that we've seen in both my first two talks. And the Dirichlet class number formula in this context says that the leading term, I've written it at 0, the derivative at 0, this is 0 at 0 because chi is an even character, and the leading term is the derivative, is negative 1/2 times the logarithm of this circular unit. So logarithm is just defined, I call it log sub infinity, via the embedding of k into C. We take the log of the absolute value, that gives a map, and then if we extend by linearity to the tensor product with q, so tensor product with q bar is embedded into C, so just sort of take a log absolute value of something and then multiply it by the factor here, which is of course consistent with the fact that log of a to the b is b log a. Okay, so you extend by q bar linearity to a map on all of this tensor product so it can be applied to an element of u chi, then this is well defined. Okay, and for simplicity later in the talk, I don't want to deal with this factor of negative 1/2, so I'm just going to let c chi be u chi to the negative 1/2. Which negative 1/2 just means multiplying by the factor here by negative 1/2. Okay, so that's Dirichlet's unit theorem, which again I stated in both of my previous two talks. Okay, now I want to move on to modular forms. Okay, so the slight generalization of the L-series of an elliptic curve that I talked about in my last lecture, I want to speak more generally about a modular form. So now it's no longer necessarily weight 2 and with rational Fourier coefficients. It has arbitrary weight and arbitrary Neven type character. But I assume that the weight is greater than or equal to 2. And I assume that it's an eigenform. And I'll recall the L function, which is just the sum of an over n to the s, which, because we've assumed is an eigenform, has an Euler product factorization. Okay, and to make this work sort of for all p, I should assume that if the Euler product really is just linear, so if p is really in the level of this f, the minimal level of this f, then I should by fiat make chi of p equal to 0. Okay, and in that case, in this factorization, I'll just take beta p equal to 0. So this is kind of consistent for p, dividing or not dividing the level of f. So I'm not assuming that this n is necessarily the minimal conductor of f for now. But okay, so this is the Euler product formulation of the L series of f. Okay, so these kind of little annoyances with these p's I'll kind of gloss over as we go forward in the talk. But so we have the L function of the modular form f that's just given in a simple way by the Mellon transform of its Q expansion. Okay, so you just take these coefficients and you replace Q to the N by divided by N to the S, and that's the L-series. Okay, now there's another L-series that we can associate to this modular form, or excuse me, to two modular forms, which is called Rankin L-series. Okay, and just defining it directly in terms of the Euler product is if I have another modular form which has some other weight and character, then you take sort of all possible products of alpha p of f and alpha p of and beta p of f with alpha p of g and beta p of g. Okay, so it's a degree 4 Euler product, so it doesn't fit on one line, so I broke it up over 2. Okay, more conceptually what's going on is that the L-series of f is associated to this compatible family of L-adic representations associated to f, which you might call rho f or rho sub fl. And similarly for G, then this is the L-series associated to the tensor product of those two representations, or those two L-adic families of representations. Okay, so that's more conceptually what's going on. The reason I say imprimitive here is because I'm not really doing what I just said in terms of the L-adic representations. I'm just forcing this to write down these products in terms of the alphas and betas, which at a good prime is the exact same thing, but at a bad prime, where one of the betas might be 0, then you might not get exactly the same thing, which is a slightly subtle issue. For example, if you have additive reduction. But again, I'm going to gloss over those. So for this is the essential part, up to some finitely many terms, which makes the difference between imprimitive and primitive. So similarly, if we just have one modular form f, not two, we can look at its symmetric square L function, which again would be associated to the symmetric square of the L-adic representation associated to f. So if that representation has eigenvalues alpha and beta, then the symmetric square has eigenvalues alpha squared, alpha beta, and beta squared. Okay. Now one thing you notice is that if f is equal to g in the previous slide, then these are three of the terms that occur in this Euler product. If f equals g, this is alpha of f squared, this is alpha beta, and this is beta of f squared. There's just one extra copy of alpha beta. Now alpha times beta is chi of p times p to the k0 minus 1. That's the weight of f. So the product of those is just the L function of the character of chi. So that's what we say on this slide, is that the L function of f tensor with itself, just from the Euler product that I've given you, three of the terms fit into this symmetric square, and the other one that's left over is exactly this. And this k0 minus k0 plus 1 comes from the fact that alpha times beta is chi of p times p to the k0 minus 1. So there's shift of k0 minus 1 in the parameter here. Okay, and more conceptually, in terms of these L-adic representations that I was mentioning, this arises from the art formalism from L-series. So this is for the primitive L-series now, so you have the right factors at the bad primes, which I've sort of glossed over in my Euler product description. More conceptually, it follows from art formalism of L-series combined with just a general fact in representation theory. If you have a two-dimensional representation, then it's tensor squared. Well, it's usually the symmetric square plus the alternating square, but in the case when it's a two-dimensional, the alternating square is just the determinant, which for the representation associated to f, as I said, is the Nebin type times cyclotomic character to the k minus 1 power. The L-series of this is just the L-series of chi shifted by k minus 1, that's this, and the L-series of this is just this L-series here. So that, and art formalism tells you that the L function of a sum is the product of the L functions. So that explains this factorization formula. Okay, so the main theorem which I want to state today, which I put in quotes because it's not been proven, and the main reason that the proof isn't complete is that it's relying on some works of others that aren't complete. So I'm kind of waiting for these results, but I'll outline the method of the proof, which is an analogous factorization for the p-adic analogs of all of the L-series that I've been discussing so far today. So the p-adic L-series of the Rankin product of f with itself factors as the p-adic L-series of the symmetric square of f with the p-adic L function of Leopoldt p-adic L function associated to chi inverse. Now, I just want to mention that this looks a little different than what I had on the classical factorization. I had LP of chi and s minus k0 plus 1, but the L function of chi and s minus k0 plus 1 is related to the L value of chi inverse and k0 minus s via the functional equation. And because of the branch of the p-adic L functions that I'm taking in this talk for convenience, it's more convenient to write it this way. Okay. So this is the factorization theorem. So this is completely analogous to the classical factorization. Okay.
Is that such kind of decomposition in non-ordinary case?
Yes. Yes. This is just I'm using Hita families, which is why I have ordinary condition. Right. Okay. So I just restated the formula here. Let me make some remarks about the theorem. So the first, right, so the first is that, as I said, there's some issue of branches of the p-adic L function, which is why it appears in this form here. And really, this factorization should be taking p-adic L functions in general should be viewed as functions not on ZP, and we've seen this in several other talks. So you can view it as functions ZP, but it's more natural to view them as functions on the weight space. That was introduced first, I think, in this conference in Coleman's talk, the continuous homomorphisms from ZP star to CP star. And if you want to understand this factorization in weight space, and I'll spend a good deal of time talking about weight space and how to view these as functions on weight space in a moment, but let me just say for now that the branch that I'm taking in order to write down this equation is when k0 is even. That's implicit here because I'm taking the cuboidal Leopoldt p-adic L function of chi, so chi better be an even character. So f, which had weight k0, had better have weight, even weight, if its Nevin type is even. So
about the question in the non-ordinary case, is the p-adic L function on the left-hand side constructed in that case?
That's a good question. Yeah, so I should have said, I'm not fully sure, yeah, because this p-adic L function, Rankin L function, was constructed by Hita, again using Hita families. But it may or may not be, but certainly it's expected to exist. And so so I mean, one should, yeah. So you can, hope to define them using Coleman families or, other generalizations of Hita families and working on the eigencurve. But I think that that's probably not necessarily written down yet. I'm not sure if anyone else knows. So, yeah. Okay. So, though I should say that the method that I use, ordinary is not just because I'm using Hita families and a technical thing, and if you just formally plug in Coleman families, it'll go through. Ordinary is actually used in a more important way, and it's not in my work, but in the work of Bertolini and Darmon that I apply, and I'm not sure whether their method could be generalized. Probably, or possibly, but there's something significant to be done to go for the method of proof in terms of the expectation of the theorem. I'm sure that it's expected this to exist and the factorization to hold. Okay, so again, so I was just discussing some technicalities about the branch. You want to make sure k0 is even, and then s, which is actually an element of this weight space, which, as I'll explain, is p minus 1 open unit disk. You want to take the disk corresponding to being congruent to k0 minus 1. Okay, so all right, so now let me say something, maybe the most important point about this theorem is that why is this not obvious from the classical factorization theorem? And the reason is that this L function, or this classical L function, has no critical values. So I'll explain in a moment. Critical values are the types of points at which you can interpolate. So this p-adic L function is not defined by interpolating a classical L function. So this definition of the L function is subtle, and the theorem cannot be proved simply by interpolating a classical factorization. Okay? Because this is not defined by interpolating this. Okay. So that's the next point, that the theorem cannot be proved by simply interpolating the classical factorization formula. And the final point is that this factorization was, in a slightly different form, conjectured by Craig Citro in his PhD thesis. Craig was a student of Hida's. Okay, so let me discuss this issue of critical values, what I was discussing in the previous slide. So p-adic L functions are typically defined by interpolation of special values of classical L functions. And the values that you interpolate are usually called critical values. So what's a critical value? It's a point such that none of the gamma factors in the functional equation at that point, or on its image point in the functional equation, has a pole. And that's called a critical value. And typically when you have such a value, then if you divide out by the appropriate period, then the value of the L function is expected to be algebraic. And those are the values that you interpolate to make a p-adic L function. Okay, so as an example that we've seen in virtually all of the talks of this conference, the Kubota-Leopoldt p-adic L function is made by interpolating the critical values of Dirichlet L functions. So when are these values critical? They're critical L of chi 1 minus n. This is what you usually take n greater than or equal to 1. When chi of minus 1 is minus 1 to the n. So if chi is an even character, then when n is even. Okay, and that's why, if you want to interpolate it for all n, why we see this twist by the omega that changes the parity for one thing. Okay. So again, this is a little bit of review. The Kubota-Leopoldt p-adic L function, which is defined when you have an even Dirichlet character, and you have this omega, which is the Teichmuller character. But there exists a unique p-adic meromorphic function, okay, which is actually analytic unless chi is a trivial character, such that the interpolation property is interpolating these critical values. Right? So this character here and this integer 1 minus n for n greater than or equal to 1 satisfy the criticality condition of parity that I said, that this to the power of negative 1 is equal to negative 1 to the n. I mean, this applied to negative 1 is equal to negative 1 to the n. So that's when n is even. And then there's always this Euler factor that you have to remove, the Euler factor at p in the Euler product expansion of this L function. And those interpolate, and that's the Kubota-Leopoldt p-adic L function. And an important point I'll make that we'll use later is that the p-adic zeta function, so when chi is the trivial character, this is not analytic, but it has only one pole, and that's at s equals 1, and it's a simple pole with residue 1 over 1 minus p. This residue can be explained because that's what this Euler factor is. If you plug in, I guess, n equals 0, then that's exactly what this Euler factor is when chi is the trivial character. So that's what you would expect. Because the classical zeta function has polar residue 1, so somehow what you're picking up is that Euler factor. Okay, and Leopold's theorem, which again I stated in both my previous two talks, is a p-adic analog of Dirichlet's class number formula, which tells you that the value at 1 of this p-adic L function is equal to some constant times the log p of the unit for which the classical L function was the log infinity. Right? So it's just a p-adic analog. And maybe I'll explain these factors. You can actually intuitively explain them. This term comes from the Euler factor, as I explained, at s equals 1. And this comes from the functional equation. I'm looking at the value at 1 of chi inverse rather than the value at 0 of chi. So you'd expect some Gauss sum which shows up in the functional equation. Okay. All right, so this is the Leopold's theorem as I explained last time. Okay. Now I should say that, so that's the p-adic L function. So there's three terms in this factorization formula. I want to explain all the three p-adic L functions. So there was the Rankin L function, the symmetric square L function, and the Dirichlet L function, or the Kubota-Leopoldt. So the Kubota-Leopoldt p-adic L function I just explained. Symmetric square L function, I'll say that it's not that there are infinitely many integers s that you can interpolate. This actually has finitely many integers s that are critical values. They're the s in the range from 1 to k minus 1, satisfying a certain parity condition. But to make a p-adic L function, you have to interpolate infinitely many numbers. You can't interpolate finitely many numbers to make a p-adic L function out of it. So the way that you do it is you introduce a character that you twist by. Okay, so psi typically here you would take a p-power conductor Dirichlet character, and there's a parity condition on it. and then these values are critical. So remember I said for a critical value, if you divide out by the appropriate period, which is given here, is the Shimura period associated to f, then you get an algebraic number. And these are the values that you can interpolate to make the p-adic L function. Now I didn't say exactly what that means, right? So how do I define, how do I interpolate these values when there's only finitely many integers being involved to get a function on ZP? Well, I'll explain that later. But for now, I just want to explain what is the infinite collection of values that you're interpolating, and it's these. Okay. Now, if f and g have the same weight, this L function has no critical values, this Rankin L-series. So in particular, if f is equal to g, if I have the tensor product of f with itself, then I have no critical values. So actually, maybe I want to pause. Can you see this, or is it better if the lights are dimmed here? Is this clear? It's fine. It's fine. Okay. Okay. So this has no critical values if f equals g, and if the weight of f equals the weight of g. So in particular, if f equals g, it has no critical values. Okay, but it does have critical values if the weights are different. Okay. So let me just say now, how do you define a p-adic L function associated to this L function? The idea, which is useful in many other contexts as well, is you view f and g as being just one element of a parameterized family, such that at other points in the family, you have critical values. You make a p-adic L function there, and then you specialize the family back down to f and g, where you started, and then you can define the p-adic L function of f tensor g as that. Okay? So to do that, we're going to have to discuss Hita families. These are the families that are going to interpolate f and g. So a Hita family for us, and this is not the correct full definition, but it's just a working definition that I can use in this talk. Okay? Is a Hita family is just a formal Q expansion. So the coefficients are p-adic analytic functions of a weight variable k. We normalize it so that the first Fourier coefficient is just 1. Okay? So each an of k is a p-adic analytic function of zp, with the remarkable property that if you plug in an integer k that's greater than or equal to 2, then the values of these analytic functions are all algebraic. Okay, and since they're algebraic, I can view them as complex numbers if I choose. And then this Q series is actually the Q series of a classical modular form. Okay, and the Hita aspect of it is you insist that that modular form is a p ordinary eigenform. So it's ordinary at p. So this concept was generalized by Coleman to remove the ordinary condition. Okay. All right. So this is the notion of a Hita family, and so these are the families that we're going to use to interpolate our modular forms f and g. Okay. So this is how Hita defined the p-adic Rankin L-series of f tensor g, in particular when their weights are the same and there are no critical values. So the theorem so I should have cited Hita here. Sorry, this theorem of Hita's is that there exists a unique analytic function of 3 variables, k, l, and s. Okay, such that, and this is important to notice this range. So L and K are the weight variables. So L is the weight of G and K is the weight of F. So that when you specialize F and weight K and G and weight L, such that K and L satisfy this inequality, notice that this implies that K is strictly bigger than L. Right? So they can't have the same weight. And S is some integer between them. Okay, and that there's some parity condition, okay, that this value of this p-adic L function that you're trying to define, this 3 variable thing, is the classical Rankin L-series of f and g at those weights at the value s divided by the appropriate period. And as usual, you have to exclude some Euler factors that were too complicated to write down on the slide. So this is the p-adic L function of the 2 Hita families, f and g. It's a 3 variable L function, 2 weight variables k and l, and one sort of cyclotomic variable s. Okay, And I want to point out a couple things. So first is that note the asymmetry between f and g in this interpolation property. I'm taking the weight of f to be greater than the weight of L. Greater than the weight of g when I specialize. Okay, and accordingly, the period they have to divide out by is kind of the relationship between f and g is not the same. You take the Schmor period of f, and then g shows up only in the power. The weight of g only shows up in the power of 2 pi I that you take. So you can see already in the period that's asymmetric, and in the weights that we're specializing to, it's asymmetric. And so there are actually two p-adic L functions, Rankin L-series, you can associate it to f and g. There's the one where you put f first and the one where you put g first. So if you put f first, then I put a little f there to make you could say that f tensor g is not the same as g tensor f. That's a little bit, you have to be careful about that. So just to really indicate that f is playing a special role, you put the f here. So to me, this is kind of analogous to if you have a single modular form, there's two p stabilizations that you could try to put through p-adic families. There's f alpha and f beta. F alpha and beta are the two roots of the Hecke polynomial at p. Similarly here, there's kind of two p-adic L functions that you could write down. Okay, now this is not going to be an issue for us when f is equal to g. Okay, so then the lack of symmetry doesn't matter. So there'll be just one, and I'll write that as LP of f tensor f. Okay. So now I want to give an application of this factorization theorem. This is actually my initial motivation. I was working on Greenberg's conjecture on trivial zeros, and that's what led me to the factorization. I sort of realized the relationship between the factorization and Greenberg's conjecture. So to state this application, I'm going to assume that chi is just the trivial character. Remember, this was the Nebin type of my modular form f. Okay, so in that case, and in general, all you have to do is twist everything by chi inverse. So I don't want to do that. So let's just assume that chi is trivial. So it still works with general Nebin type. It just makes the notation more complicated. So it turns out that this LP of sim squared f has a trivial zero at s equals k minus 1. So remember, this is exactly the type of thing I was discussing in my previous talk. And what a trivial zero is that the value of this LP of sim squared at 1 is an Euler factor times the classical value of L of sim squared at 1 divided by a period. Now that Euler factor turns out to be 0. Okay, and that's a trivial zero. So it's kind of, this thing is 0 for a silly reason, namely you multiplied it by 0. Okay, so when you have a 0, you should ask what's the value of the derivative. So what we define to be the analytic L invariant, using following the notation I described in my last lecture, is basically the derivative at that point was a trivial 0, so at k0 minus 1, and sort of normalize it by dividing out by the algebraic part of the classical symmetric square. And there's a star here, and what that star is actually is you also want to, I guess, divide out by the Euler factors, the non-zero terms in the Euler factor of this interpolation. So this interpolation has a few Euler factors you take out, and you ignore the ones that are 0 at that point and divide out by the ones that are non-zero. And that's what you define the analytic L invariant to be. Now Greenberg defined an algebraic counterpart to this analytic L invariant. Just as we saw for an elliptic curve with split multiplicative reduction in the last talk, I defined the analytic L invariant to be the derivative of the p-adic L function at 1 divided by the algebraic part of the classical L function, and defined an algebraic counterpart, which was an element of a cohomology class in the Tate module of the elliptic curve. Similarly, in general, there's an invariant of the corresponding representation. So you would expect that it would now be an invariant of the Gauss representation associated to the symmetric square of f. And then there's this twist by 1 minus k0 to kind of move this point to 0. Okay, so there's an algebraic counterpart, and what Greenberg conjectured is that these two are equal, just as he was able to prove with Greenberg and Stevens in the case of an elliptic curve with split multiplicative reduction. So this is what I described at the end of my last talk as the next case of the trivial zero conjecture. Okay, so now what has been done on this? Well, just as in for the split multiplicative case, there's a link between the algebraic and the analytic, which is provided by the Hita family. So that I call the Greenberg-Stevens L invariant of the symmetric square of f, which is the derivative of the pth Fourier coefficient of the Hida family F at the point you're interested in, k0, divided by AP of k0. So this kind of divided by AP of k0 didn't show up last time because I was assuming this number was 1. But in general, this is what the L invariant is. And it's interesting that it's the same L invariant as the one that shows up just for F itself. Okay. And what Hida proved under some assumptions, and then Robert Heron proved unconditionally in his PhD thesis, was that the algebraic L invariant can be calculated by the analytic L invariant. Or excuse me, by the Greenberg-Stevens L invariant, by the derivative of AP. Okay? So this is sort of the link between the Hida family and this Galois cohomology class. And the link is provided by, again, the theory of Hida and Wiles of ordinary representations and lambdatic representations. So that's the method of proof here. And the relationship between the factorization theorem that I stated, or I'm working on, I should say, is that from this factorization theorem, it would follow that the analytic L invariant is also calculated by the same Greenberg-Stevens L invariant, and therefore we'd get finally a proof of Greenberg's conjecture by saying that the algebraic is equal to the Greenberg-Stevens is equal to the analytic, therefore these two are equal. Okay? So the fact that this factorization theorem implies Greenberg's conjecture was actually already known to Citro, and that's what he proves in his paper where he makes this conjecture of the factorization theorem. And because this is very cute, I just want to point out one aspect of the proof of that the factorization theorem implies this corollary of Greenberg's conjecture. So I just want to, I'm not going to give the full proof of that, it would take a little too long, but I just want to give one aspect of it. And that is, well, we have this factorization, which in this case looks this way. So remember, the p-adic L function of F is just, by definition, the p-adic L function of the Hida family specialized where the weight variables are both k0. Okay, so if I plug in my S to be k0 minus 1, the interesting point where I have this trivial 0, then here I get a trivial 0, and here I get the p-adic zeta function at 1. Now the p-adic zeta function at 1 has a pole with residue 1 minus 1 over p. So this pole cancels with this 0, and you get the derivative that you're looking for times this residue, which is some simple factor. So this is basically the analytic L invariant up to, well, the algebraic part of this L function and this residue here that's here, and then the Euler factor. So up to some algebraic constant, this is the interesting part of this value. So then you ask if you can calculate this some other way so that you get the Greenberg-Stevens L invariant come out. Then you would prove that this is equal to the Greenberg-Stevens. And you can, it turns out. So instead of restricting to the line k equals L, which is what I've done here, okay, in my factorization, what you can do is you can restrict to the line S equals k minus 1, okay, and let L vary. Then it turns out that a factor of 1 minus AP of L over AP of k factors out, okay, and then what's left, it turns out, has a pole. And so what you get again is something that when L equals k0 has a 0 times something that has a pole. And so you get the derivative of this times the residue of the other thing. The derivative of this is exactly AP prime over AP at k0. And then the residue of the other thing turns out to be all the algebraic factors that make this work out. All right? So that's the sort of cute trick that allows you to prove Greenberg's conjecture from this factorization. Okay, so now I want to talk about, the rest of the time I'll talk about how to prove this factorization formula. So the method that we follow in this work is a method of Gross, who proved a similar factorization of Katz's p-adic L function when you have a character of your quadratic imaginary field that is the restriction of a Dirichlet character. So a abelian character of Q, you restrict it to the quadratic imaginary field. In that case, the Katz p-adic L function factors as a product of two Kubota-Leopoldt p-adic L functions. Okay, so in this factorization, epsilon is the quadratic character of the field K, and chi is your arbitrary even Dirichlet character. Now again, in this theorem, I'll point out that the left side has no critical values. So this is not defined by interpolating anything directly. You have to put this into a two-variable family that has special values, and then you specialize back down outside the range of interpolation to get this left-hand side. Okay, so this again cannot be proved by interpolating classical values, classical interpolation, right? Because the L function of a character of a quadratic imaginary field, that's the restriction of a Dirichlet character factors, again, as two Dirichlet L functions from the Artin formalism, but that's not how you prove this. Okay. So now to say how you prove this and how you prove, my analog with the p-adic Rankin L-series, I'm going to discuss a little bit the weight space, because that's an important feature because you don't have, because you don't have critical values that are integers that you can plug in. It turns out to be important to be able to twist by characters, and to do that I want to discuss weight space. So weight space, an element of weight space is a continuous homomorphism from ZP star to CP star. Okay. Now what does a homomorphism look like? Okay, so this sort of get down and dirty with how do you understand what an element of weight space is? Well, if you look at 1 plus p, that's a topological generator of 1 plus pzp, which is a big chunk of this zp star. Then by p-adic continuity, that 1 plus p has to go to some element of CP star whose distance from 1 is less than 1. Okay, so x minus 1 has to have absolute value less than 1 for this to extend to a continuous homomorphism. Okay, so given an element in weight space, you have a maybe not canonical because 1 plus p is not so canonical, but you have an element of the open unit disk in CP it's associated to it, namely just the value of phi of 1 plus p. Okay? And that determines phi on all of 1 plus pzp by continuity, because any element in 1 plus pzp can be written as 1 plus p to some p-adic power. And so the image of that element in 1 plus pzp is just the image of 1 plus p to that p-adic power. Okay? So that determines phi. So we have this sort of open unit disk in CP that classifies the possible values of phi of 1 plus p. And once I know phi of 1 plus p, which can be any element in the open unit disk in CP, how much is left to determine what phi is? Well, ZP star is generated as a group by 1 plus pzp and the roots of unity. So if you have a p minus first root of unity, then there aren't too many options for where that can go either. It has to go to another p minus first root of unity. So that's just classified by some element in z mod p minus 1. Z mod p minus 1. So therefore, the weight space can be viewed as the disjoint union of p minus 1 open unit disks. So each unit disk tells you, the point in the unit disk tells you where 1 plus p goes, and which disk you're in tells you where a root of unity goes. It goes to zeta to the a for some a mod p minus 1. So it's p minus 1 open unit disks. Now we can identify certain special elements in this weight space. Okay, we can identify certain special elements in this weight space. So first of all, we have integers. So any integer gives me a continuous hom from zp star to zp star, which then I view as a subgroup of cp star, just raising x to x to the k. And the integers form a dense subset in the rigid analytic sense of weight space. Similarly, for any Dirichlet character of conductor power of p, you have an element of weight space, namely zp star. You can project onto this quotient to z mod p to the r z star, and then you apply alpha, which is a Dirichlet character, and we fixed an embedding of q bar into cp star, so then you can view this alpha, which we still denote by alpha, as an element of weight space from zp star to cp star, and it's clear this is a continuous map. And the set of such alphas are also a dense collection in the sense of rigid analytic sense of weight space. Okay, so there's two different ways. So this is how we can define a p-adic L function using Dirichlet characters, using twisting by Dirichlet characters, because they form a dense subset of weight space. You don't have to use a dense collection of the integers. That's one way with the Kubota-Leopoldt p-adic L function. But most p-adic L functions are defined interpolating characters this way. Okay. So as I mentioned about this sort of branches of p-adic L function, so if you fix one of these disks, in these p minus 1 disks, then you can embed not just z, but zp into weight space via, this is the projection, this bracket x is the projection onto the 1 unit part. Okay, so x divided by omega of x. So raising that to the nth power, and then you just fix yourself in a specific disk of the weight space by taking the 8th disk. Okay, and this is consistent with the embedding of z into a weight space for integers that are congruent to a mod p minus 1. And all 3 p-adic L functions, and most p-adic L functions, are functions on weight space, not just Zp. Okay, to be purely formal, the Hida-Hecke algebra could be a cover of weight space, and then it would be a function on that cover, but I don't want to deal with that. I just want to assume that sort of the Hida-Hecke algebra is lambda, in which case we have weight space. Okay, so our theorem from the perspective of weight space, now that I've taken out the ZPs, right? So if I state it as ZP, which has been thought of in p minus 1 different ways as a subset of weight space, the real proper way to state it without choosing this branch is just state the equation on weight space. And then our theorem is this. So the weights are now written with Greek letters rather than sort of, English letters, K and S. I have kappa and sigma. So the equation, which is the same equation, which is that the LP of FF kappa kappa sigma, so along this diagonal where the weight of K equals the weight of L, so I'm sort of tensoring the same modular form with itself, that's when I expect this factorization. And then sort of K minus S becomes kappa sigma inverse. Okay, so that's the way to state the theorem in weight space. So for the rest of the talk, I just want to take the simpler case when this Nebben type character that I started with of my form, which is this capital F specialized in weight K0, I assume that that's trivial, just so I can write it as the p-adic zeta function. Okay. So instead of proving this equality for various integers so that I can say that interpolating I get the equality on all of Zp, I'm going to prove the equality for certain elements that are twists of Dirichlet characters. So if I can prove the equality for kappa and sigma of a particular form, say kappa is x squared times alpha of x and sigma of x is x times beta of x, where alpha and beta are Dirichlet characters of p-power conductor, well, these are all dense in weight space too. Okay, I said that the Dirichlet characters themselves are, but if you just translate them by, multiply them all by a certain point, that's not going to change the density. Okay, so these are all dense. So I can prove the equality for kappa and sigma specifically of this form, and then by p-adic continuity deduce the result for all of weight space. So for the rest of the talk, again, I'm going to make some simplifying assumptions. So I'll take beta equal 1, and I'll take alpha to be an even Dirichlet character of conductor some p to the r. Okay, so I'm going to describe how to prove this equality under these assumptions. If I prove this for this generality, I would get it for a dense collection on W cross W, and I would get the equality. So I'm going to just, to say how to prove it simplicity, I'm just going to take these examples. Okay, so again, my weights are kappa of x equals x squared times alpha of x, where alpha is an even Dirichlet character, conductor p to the r, and sigma of x is just x. So that corresponds to the point s equals 1. Sigma of x equals x to the 1. Okay. Now, these Hida family, remember I said that it's sort of indexed by elements in Zp. Actually, this lifts to weight space also. And so when I plug in one of these kinds of weights rather than just an integer, right, so the kappa of x equals x squared would just be the integer 2. So that would give me a weight 2 modular form, I said when I defined Hida families. But more precisely, when you specialize to kappa equals x squared times alpha of x, you get a weight 2 modular form of conductor n p to the r and Nebben type character alpha. Okay, so that's how alpha shows up. So our desired equality at the point that we want, so the desired equality being this one, okay, when kappa of x is x squared alpha of x and sigma of x equals x, that desired equality in terms of this modular form lil f, which is a classical modular form of weight 2, okay, so this desired equality then reads the p-adic L function of f tensor f at 1 is the p-adic L function of the symmetric square of f at 1 times the p-adic L function of alpha inverse at 1. Okay, so the Komodo-Leopoldt p-adic L function of kappa sigma inverse, so kappa sigma inverse is x goes to x times alpha of x. So x times alpha of x that goes to the x part means the value at 1, and times alpha of x, it turns out, means you take the p-adic L function of alpha inverse. Okay. So now let's just see, okay, we have to understand the three sides of this, the two sides of this equation, each of the three terms involved. So let's just study them one by one, what we can say about it. So this is what we're trying to prove for the rest of the talk. So the simplest one is the value of the symmetric square. Okay, so I said that the left-hand side, that the part of my equation was non-critical, and it's not a critical, but, and the right side overall is not critical, but this piece of the right side, it turns out, is critical. Okay, so that's a critical value. So it's an interpolation. If you look back at when I said you can interpolate, it turns out that this is a critical value, and this is just an algebraic number, the algebraic part of the classical L function. So that's the simplest of the three terms. Okay. Meanwhile, I told you what the value of the p-adic L function of alpha inverse at 1 was at the beginning of the talk, and in both my previous two talks. That's Leopoldt's theorem. It's the p-adic log of a circular unit times some fudge factor, which I won't bother writing down. Okay. So what do we have now? Okay. Let's go back. This right side, what is it? It's some algebraic number times the log of some unit, p-adic log of some unit. So what I want to do is now show that the left side is the p-adic log of some unit. Okay? So what we need to show is that the left side is the p-adic log of some unit, okay, in the same u alpha, okay? And we need to show a relationship between this unit and the other unit, which is that this unit is the other unit to the power of, the extra term coming from the symmetric square. Remember, to the power means just multiply on this right tensor factor by that number. Okay, and then all your fudge factors better work out too. So that's what the star is saying. Okay, so does everyone follow that? So basically, if this is equal to the algebraic part of the symmetric square, and this is log p of c alpha, then I need this to be log p of some other unit that's equal to c alpha to the power of what this constant is, right? And then I'll be done. All right, so now I need to tell you how to define such a unit. Okay, so the way we're going to define such a unit is using intersection theory of higher Chow groups on certain algebraic surface. So the surface that we're going to take, actually I'm not telling you the surface now. First I'm just going to tell you about intersection theory, and then I'll tell you how we're going to apply it. So let S be any surface, say over, it doesn't really matter that's Q, over any field. And we have the usual Chow group of S, which is just, you can think of as formal linear combinations of irreducible curves on S, modulo rational equivalence. Okay? So that's just the usual Chow group. Okay, and now what Bloch defined is sort of generalizations of these Chow groups. This is a higher Chow group, Chow2 of S1. Now what is that? So Chow2 of S1 for a surface S is a formal linear combination not just of an irreducible curve, but of the irreducible curve paired together with the function on that curve. And the condition that the functions have to satisfy is that the sum of the divisors has to be 0 on the surface. So each curve has its own divisor, which won't be 0. It'll be some 0 set minus some polar set. But these curves can intersect one another in the places where the divisors are supported in such a way that the divisor, the pole of one function on one curve, cancels the 0 of another function on another curve. So you want the sum of the divisors on each of the curves to cancel out perfectly, so you get 0. And then there's some equivalence relation that comes from K2 of the surface that you have to mod out by. Excuse me, K2 of the surface that you have to mod out by. These are called tame symbols. All right, so I won't get into that. But the point that I want to make, or what I'm going to use, is that there's an intersection pairing between these two, okay, which can be described elegantly just in terms of intersection on the surface. So by GM, I just mean the multiplicative group. So if you have an element defined over, if you have elements defined over a certain field, then the intersection lives in that field. Okay, so they're just saying this into Galois equivariant map, and the intersection pairing is defined by taking a curve on S, that's the Z in the Chow 1, and you could take say a sum of curves with functions on them. And what you do is you physically intersect the curve z and the curve zi. That's two curves intersecting on a surface. They'll intersect in some points. Okay, and you take the product of the functions that you had at those points. Okay, and of course you have to choose your representatives of these classes so that they intersect properly, and so that the intersection points avoids the zeros and poles of the UIs, so that these are not zero infinity, and that's the intersection product. Okay, and Bloch defined more generally intersection pairing on higher Chow groups, and this is just a special case. Okay. Okay, so the case that I want to apply this to is the case where you take a modular curve, the modular curve on which your modular form f sits, x1 of np to the r, and the surface will just be the self product of that modular curve with itself. And so I'm going to define for you an element of Chow 1 of s and an element of Chow 2 of s comma 1, and I want to intersect them, and that's going to be my unit that showed up in the theorem, giving me the special value of the p-adic L function of f tensored with f. Okay, so the element of Chow 1 is going to be defined essentially as the idempotent in the Hecke algebra corresponding to f viewed as a correspondence on s. Okay, so you can view elements of the Hecke algebra as correspondences. So for example, TL, what would it be? Well, for each point on your modular curve, it has L plus 1 isogenous curves, and that gives you L plus 1 points on the second copy of x cross x that it corresponds to. And as your point moves along the modular curve, you sweep out sort of a degree L plus 1 correspondence on this product of modular curves, and that would be sort of Z associated to TL. Now, if you take your Hecke algebra and tensor it with Q bar, then there's projection onto the component where the Hecke algebra acts via the eigenvalues of f, and that's what I call TF. And that element of the Hecke algebra gives me some gives me some correspondence on this curve on Chow 1 of s tensor with Q, and I call that TF. And I actually want to hit that Hecke operator with another Hecke operator, which is the Atkin-Lehner involution, which plays an important role. And so that gives me an element of Chow 1 of s. This Atkin-Lehner actually took me the longest part to figure out that that's what I needed to make things work out. Okay, so this Chow 1 of s is this element of Chow 1 of s associated to f is going to be paired now with a certain class in Chow 2 of s comma 1. Okay, so there's a certain class that has been called the Bailenson-Floch class, because it sort of appears in the work of Bailenson and also in Floch's study of the symmetric square L function. So this is a certain element in Chow 2 of S1. And remember, what is an element of Chow 2 of S1? It's a linear combination of curves on S with functions on S. So the curves that you take are actually pretty simple in the definition of the class. They're just the diagonal. So x diagonally embedded in x cross x, with horizontal and vertical copies of x. So x cross a point and point cross x. And on each of those horizontal and vertical and diagonal copies of x, you just place a modular unit associated to alpha to the minus 2. Okay, this sort of modular unit you can associate to any Dirichlet character. And that's the one that you take to be your function, and that you organize them in such a way that the zeros and poles cancel out and you get an element of Chow 2 s comma 1. So I won't define it precisely, but that's the Bailenson-Floch class. And then my unit that I want to define now is just the intersection. So the intersection pairing that I defined between Chow of s comma 1 and Chow 2 of s comma, Chow 1 of s and Chow 2 of s comma 1 gives me an element of Q bar star. And since my elements are actually tensored here with Q and in the previous case with Q bar, I actually get an element of Q bar star tensor with Q bar. Now, the first proposition that you have to prove is that this is actually an element in U alpha, the unit group that you cared about. So there's two aspects of this statement. One, why is it a unit? Why is it not just some element of Q bar star, but why is it in O Q bar star? And secondly, why is it defined over K, and why does Galois act on it by alpha inverse? So let me explain those both briefly. So the fact that it's that it's a unit comes from CM theory. So as I said, the essential point of this delta, I mean, the essential part is this diagonal. So what happens if you intersect the diagonal with a Hecke correspondence? What are the points that show up? So in the moduli interpretation, this means it's an elliptic curve that's cyclically L isogenous to itself because it's on the diagonal. And what kind of elliptic curves can you have that are isogenous to themselves via cyclic isogeny? Only CM elliptic curves. And I said that the function was a modular unit. So now this is classical CM theory that a modular unit applied to a point that corresponds to a CM elliptic curve is a unit in some abelian extension of a quadratic imaginary field. Okay? So forgetting the field of definition, at least I know that it's a unit. Now why is it defined over the appropriate field with the appropriate action? Well, I said my pairing is Galois equivariant. So it turns out that ZF is defined over K with Nebin type character alpha, and that's because I projected on that's because the Akin-Lehner is defined over K and Galois acts via the diamond operator, and I projected onto the F isotypic component where the diamond operators act via alpha. So that is defined over K with character alpha, and this is defined over K with character alpha to the -2, so the intersection turns out to be defined over K with character alpha inverse, and that's where you get this. Okay, so this is the unit that's going to show up in my p-adic formula. So that's the theorem that you then prove, is that your p-adic L function of f tensor f at 1 is the p-adic logarithm of this unit up to some fudge factor. And so let me now explain three elements of proving that. So this is kind of the most important aspect of the proof. So the first is a theorem of Bertolini, Darmon, and Rocher. And again, I guess theorem should be in quotes because this isn't fully proved in the full generality that I need it. Okay, so they give a formula for this in terms of this p-adic or symptomic regulator that we saw the ray of light in Kwong Do's talk. Okay, so we have this p-adic regulator associated to the Balance and Flock class applied to a certain de Rham cohomology class associated to F. So omega F and eta F, a certain de Rham cohomology classes on X corresponding to F. Okay, so omega F is basically the holomorphic, is just the usual de Rham cohomology class corresponding to F, and then eta F is a unit root lift of the anti-holomorphic de Rham cohomology class, which is algebraic. So we get this, and the tensor product you view as in the H2 of S via the Coulomb decomposition as H1 tensor H1. So we get two, so the regulator of this difference turns out to give you the p-adic L function. And this is a p-adic Balancin formula. So I'll state the classical Balancin formula at the end of my talk, and this is a p-adic analog of that is proven by Bertolini, Darmon, and Rocher. And so remember I said that there is some place where we need something technical about being ordinary, and it's because Darmon, Rocher, and Bertolini use a unit root lift to define this eta F. So that's kind of an essential point. I don't know if maybe one can get around it in the non-ordinary case. I don't know. Okay, and then the second is an important commutative diagram relating the regulator map with the intersection pairing. So this gives me this in terms of the regulator map, and now I need to relate it to the intersection pairing and the p-adic logarithm. That's what this theorem says. So that's just the commutative diagram. So it turns out, I'll forward here, that the image, the reason the ZF is so important is that the image under the p-adic de Rham cycloclass map is exactly this omega tensor eta minus eta tensor omega. Okay? And there is the p-adic regulator is a map from the Chow 2 of S1, which is the same as the K1 of the surface, to the dual of the Phil 1 of the H2 de Rham of the surface. Okay, so that's related to the intersection pairing because there's a p-adic cycloclass map that goes from here to here. So if I start off with my ZF here and my delta here, then on going around this direction, I get log p of BF because I'm getting BF here when I take the intersection, then I'm taking log p. That's exactly the right side of this equation. If I go around this way, then via this last calculation, you're seeing that you're getting the p-adic regulator of delta with exactly this differential here. And so by the Bernoulli-Darmon-Rocher theorem, that's the LP of F tensor F. And there's a lot that goes into this. There's Besser's theorem that the p-adic regulator is related to the étale regulator via the Bloch-Kato exponential. And so you have to use some comparison isomorphisms of the form that we saw in Yasuda's talk, and some compatibility in this comparison isomorphisms with respect to cup product and cycle class maps in order to then reduce to some fact about the étale regulator, which you can explicitly calculate. Okay. So that sort of is a quick summary of the proof of this theorem, which is sort of the main point. Okay, so anyway, so now I want to summarize in the last 2 minutes, I guess. So the p-adic L function of F tensor itself, this was the theorem in the previous talk. And this product, remember, this was critical, which is the algebraic part, and this was Leopold's theorem, so I have this. So for equality, I just need to prove that the two units are related this way in U alpha. And I should point out that this U alpha has dimension 1, so we know that they're going to be related in some way, via some constant factor, but I just need to know that this factor is the right one to take. Okay? So how do I know that this is the right factor of proportionality between these two non-zero elements in a one-dimensional space? And then now I finally do use the complex factorization. So I kind of lied and said you couldn't use the complex factorization. It's true you can't interpolate it mindlessly, but you use it to deduce a relationship between the units that you want. So if you take the leading terms at s equals 1 in this classical factorization, okay, that follows from the Artin formalism, then, okay, so then you get that the derivative of this at s equals 1, so this has a 0 and this has a 0 at s equals 1, so the derivative of this divided by the period is equal to this algebraic part, same thing that was showing up before. So of course it should say symmetric square of f at 1. Symmetric square of f, that's all I should say. Yeah. Okay. Times, remember this was the log infinity of that same circular unit. So to finish the proof of the theorem, it remains to prove the complex analytic analog of the p-adic formula that I just wrote. Because if this left side is equal to the complex analytic log of bf, then I have log infinity of bf is this same algebraic constant that showed up in the p-adic formula times the log infinity of the circular unit, and that gives me this relationship. Okay, because this log infinity is an injective map, so this is saying that this is related to this unit by this scaling factor. Okay, so now we've boiled down to proving one complex analytic fact, which is just the exact analog of the p-adic formula that I wrote before. So that's the other theorem that you have to prove, is the complex realization. So as Kongdo said, there's these different rays of light. You have this algebraic thing, which is these Chow groups, and you have these different regulator maps, which is rays of light casting shadows, and then we're proving the equality of the special value formulas on the wall of this cave. Okay, so Balançon's formula. So the three parts exactly mirror the three parts in the p-adic formula. The first part is Balançon's formula, which I said the p-adic analog before, which is that the leading term of this tensor product of f with itself is a complex regulator associated to this class in the Chow 2 of S1 with the associated differential. So this is the sort of anti-holomorphic form whose algebraic realization unit root lift was the eta f before. So this sort of corresponds to the eta f. And then you have a commutativity just as before, where now you have sort of the usual, the real analytic cycle, Durham cycle class map, okay, which maps into the H11 of SR. And then you have this regulator here, and this is the log of absolute value. So this is the thing that gives you the log infinity. So it's the exact same picture as before. If you go around this way, you get by definition log infinity of BF, and you go around this way, then in view of this property that the Durham cycle class map applied to this cycle ZF in my Chow 1 of S is exactly this differential, then you get the left side. Okay, so that concludes the proof of this equality, which then proves that BF and C alpha are related via the symmetric square, algebraic part of symmetric square, which then proves the theorem. So I'll end there.